We know from the first law of thermodynamics that heat and work are related, and we now want to introduce heat engines. A heat engine is any device that uses heat to perform work. There are three essential features of a heat engine. First, heat is supplied to the engine at a relatively high input temperature from a place called the hot reservoir. Second, only part of this input heat is used to perform work by the working substance of the engine, which is the material within the engine that actually does the work. For example, the air-gasoline mixture in an internal combustion engine. And third, the remainder of the input heat that is not used to perform work by the engine is rejected to a place called the cold reservoir, which has a temperature lower than the input temperature. The figure below illustrates the three main features of a heat engine. The symbol QH refers to the input heat, and the H corresponds to the hot reservoir. Likewise, QC refers to the rejected heat, and the C corresponds to the cold reservoir. The symbol W refers to the work done by the engine. Since we must conserve the amount of energy or heat that is extracted from the hot reservoir, it is useful to talk about the magnitudes of the heat and work. Hence, we will consider the absolute values of QH, QC, and W moving forward. If you were to design a heat engine, you would probably want to make it as efficient as possible. This means the engine would convert as much of its input heat into useful work as it could. Therefore, the efficiency E of an engine is defined as the ratio of the magnitude of the work done by the engine to the magnitude of the input heat. Notice that if all of the input heat was converted into work, then the efficiency of the engine would be 1.00. A heat engine's efficiency is often quoted as a percentage, which is found by multiplying the efficiency E by 100%. Thus, an engine with E equals 1.00 would be 100% efficient. An engine, like any other device, must obey conservation of energy. If there are no other losses inside an engine, then the principle of conservation of energy requires that the magnitude of QH equals the magnitude of W plus the magnitude of QC. We can solve this relationship for the magnitude of W and substitute it back into the equation for efficiency to obtain the following. This allows us to calculate the efficiency of a heat engine in terms of the input and output heat. We will see in the next section that nature does not allow 100% efficient engines to exist.